Good afternoon, everyone. Welcome to our fourth webinar of this series that we have been doing on the i4Driving project. So this project title is Integrated 4D Driver Modeling Under Uncertainty. And my name is Maria Rodriguez from Pantaya. This is a research project that we started in 2022. And it's with the partners that you can see on the right side from Tier 1, from research entities, SMEs. We have quite a broad different competencies among the team, and we are closing the project in March this year. We were quite ambitious when we drafted this proposal addressing the needs from the European Commission. So our vision was to lay the foundation for a new industry standard methodology that would establish a credible and realistic human road safety baseline for the virtual assessment of the CCAM systems. And with this, we had this objective of develop a library of credible models that contain the heterogeneous human driver behavior. And these models could further support the design and be used on an evaluation framework contract. This is somehow how the project is organized. So our core part is to develop these models. And for that, we started by gathering evidence from human factors from the data. And then we had simulators and experiments that we did in real world, also to collect data, to validate, to calibrate. And finally, we are testing the models of i4Driving in these different 5 application fields. And we always remind you this. So there's a list of webinars. The last one is in the 31st of March. We have already done the 3 that you can see. With the QR code, you can register to the upcoming ones. We hope that you do. And you also have the YouTube link because we are saving all the webinar videos in YouTube so that everyone can watch them later. And today, going straight to the topic. So we have 2 speakers. We have Johan Olstam from VTI, and we have Tianyu Tang from TUM in Munich, and they will tell us about the results and what was the work done to answer the question that you see in the screen. How realistic are behavioral driver models? And without further ado, I will pass the floor to Johan, who will start, and then T will follow, and then as typical, we do the sandwich approach, and then Johan in the end concludes. And there is the moment that you will also have opportunity to make some questions. So please do write them in the chat, or if you raise the hand, I can also give you the floor and allow you to use the microphone. So please, Johan, T, good luck, and let us know what you did.
Yes, thank you, Maria. So my name is Johan Olstam, and as Maria said, we will share this together with T. And I guess maybe several of you listened to the first webinar by Hans van Lint and Klaus Bengler, where the model was introduced. If not, it is an extension of this traditional microscopic traffic simulation models, which are collision-free, and it's an addition of this cognitive layer in order to capture human deficiencies and so on, in order to be able to use it also for safety evaluations. And if you do this extension and so on, the question of course comes, how good is the model and how realistic is the model? And last week, Vincenzo Punzo presented a little bit on this on calibration and validation, where these traditional methods where you compare output of trajectories or aggregated metrics to see how well could the model reproduce real-world data, speed profiles, or aggregate metrics. And this is really nice. We get this error metrics. We can say something on how close we are to reproducing this data, but it gives a little bit limited knowledge on when there is not a perfect match, or when it's, I mean, the error will always be there. So how realistic is actually the behavior? It might be that you get low error metric, even if the behavior is not super realistic. So to complement this, we were thinking of also doing some more subjective evaluations. So the objective here we'll talk about today is evaluating how realistic the i4Driving model is of reproducing human driving behavior from a perceived point of view of a driver. We have been focusing on motorway driving because we think that's maybe where the model is most mature. So we ask us questions then, can humans distinguish the i4 driver model from a real driver? If not, what makes the behavior appear realistic or unrealistic, or why are they not perceiving it as a real driver? And we were thinking maybe we can use a version of this Turing's imitation game to study this. So Turing's imitation game is this where you interact with an agent and you don't know if it's human or computer, and you would like to see if you could distinguish whether you're interacting with a human or a computer. And such subjective evaluation can give us then more information. So we put up this 4 main different research questions. One related more to the method, to what extent is such a Turing-inspired evaluation method useful to assess driver models or automated driving. And the second one is more related to how good the model is. So to what extent can participants distinguish between the human driver behavior and the i4 driving model? And also what are the aspects of driving behavior that make them feel that it's more or less human-like? Is it the predictability, the safety, responsiveness, the effectiveness, and so on? And the last one, how can we gain insights from this in order to guide further refinement of the models? For a Turing-inspired driving simulator experiment, we thought about several different versions. The first one, which we call the interaction version, is where you drive and then interact with another or several other vehicles, which are either controlled by the model or another human. The second one would be what we call an observing surrounding version. So that's more kind of you ride a vehicle and then you observe the interaction of that vehicle with other vehicles that could either be controlled by a human or the model. And the last one being that you're driven by a vehicle either controlled by the human or the model. And we in the end decided to go with the first one, which is more close to the original Turing test as well, where you have the possibility to choose yourself how you interact with the other vehicles in order to test how the vehicle behaves in different situations. So the instructions for the participants that we had in our driving simulator was that in this experiment they will be driving in a driving simulator and where the surrounding vehicles are controlled by different automated systems. And we asked them to evaluate how human-like the behavior is. And we tell them that you don't know which automated system you're interacting with. And we limited ourselves to having interaction with one vehicle, main vehicle at a time. So that one was pink in one of the experiments and red in another one. But it was a specific color on the vehicle to interact with, and all other vehicles was white and background. And they will drive these scenarios several times so that they can test different ways of interacting with. So this means that they were actually not knowing that one of the vehicles are sometimes controlled by a human. And that was deliberately chosen in order to avoid that they look on small details trying to figure out who was human or not. And we were more interested in how they describe the behavior of the vehicles and if the description of the behavior of the human driver or the i4 driving model was different or not. And for the case with the human control agent, we used this kind of co-simulation setup, which looks something like this. So to right here, we see that we have the participants in what we call driving simulator 1. In Tomo, it was a real vehicle cabin with screens on the side to get enough field of view. In VTI, we used an extended reality setup, which this green part here is replaced by the virtual environment. And the white vehicle here driven by the participants and interacted with the agent in 3 different scenarios. And if the agent was driven by another human, it was using another driving simulator in another room, which the participant didn't know about. And in the cases it was driven by the model, it was the i4 driving model. And we had 3 different scenarios. I will tell you a little bit more about them later on. But in the first one, the agent comes from the on-ramp. In the second, you're catching up with a slower truck. And in the third one, there's this weaving segment. So we had 3 different scenarios. In TUM, we had 2 different agent types. We only considered 1 set of parameters for the i4Driving model, and VTI we considered 2. And we then did 3 repetitions of each scenario. That limit to 3 was in order to keep the time short enough for managing all these cases. Important to notice here as well that this was not done in parallel, this was sequential. So we first did the experiment at TUM, and then we learned lots of different things, and then we refined a little bit of the experiments when we did it later on at VTI. So there are some differences, but we try to keep several things similar. One of the differences is that in the TUM case, we had randomized scenario agent order. So it could be that first you drive scenario A with the human agent, and then you drive scenario B with the i4Driving model and so on. Well, we changed that to the VTI experiment where we had still randomized order, but we did 1 agent at a time. So it could be first doing the human with BAC scenarios, and then doing 1 of the agents with BAC and so on. So the 4 different agents we have considered is the human or the confederate, as it's called in Turing Test terminology. And that was staff at TUM or VTI was asked to drive as careful and competent as they could. In TUM, it was the same driver in all of the cases. In VTI, we managed to have it for most of the cases. We had to have a stand-in for some of the participants, but we have tested and we don't see any difference in results depending on stand-in or not. For the model, when we did experiment at TUM, we used the model available at that time, September, October last year, and did it with the default parameters. We had then some more time to think about parameter variations when getting to the VTI experiment. So we tried to change the parameters slightly to represent a more careful and competent driver, and maybe someone that is slightly less cautious. So the scenarios here are constructed in such a way that we have the participant, the blue ego vehicle here coming on the motorway in the first scenario, and then we sync so that the red agent vehicle will arrive more or less at the same time to the on-ramp, and some distance or time in before the control is handed over to either the human driver or the model. And then in B, it's this scenario where you catch up with a slower truck, and you can then see how to interact if you try to overtake the red vehicle before the red vehicle overtake this truck, or vice versa, and so on. And C, we have this motorway merge diverge situation where the participants comes on the left motorway and need to go to the right motorway, and the agent vice versa. And the same here, we have this synchronization so that the vehicle should be approximately arriving there at the same time, and then we hand over to the agent, or being the human or the model. We had slightly different sync strategies to get this work slightly better, so we improved it a little bit for the VTI. And we also changed scenario B a little bit, and adding several trucks with possibilities to go in between the trucks to make the interaction a little bit more lively. So the overall procedure is that, of course, we had this recruitment and having pre-questionnaires collecting information about the participants, and they had to practice in the driving simulator and calibrate eye tracking equipment and so on when arriving. But then we have the experimental trials. So in the TUM case, we had this randomized order. So you draw 3 times, for example, scenario A with a human agent. And then after each scenario, we had a post-scenario questions rating. T will guide you into the questions and answers later on. But we also had used a think aloud protocol where we asked the participants to verbalize their thoughts continuously during the driving, what they are planning to do, how do they think the vehicle behave, does it behave in a way that seems human-like, or why not, and so on. So they should continuously tell what they are experiencing. And after the complete drive, we had post questionnaires with more open-ended questions. So this is one of the changes we did to the VTI experiment, where since we did all the free scenarios with one agent before changing, we could also have a post-agent questionnaire. So we had a break after you have been driving all three scenarios 3 times, and then we asked them about the agent's behavior for all of the 3 different scenarios. And the participants in TUM, we started with the testing with using regular drivers with a mixed experience. Most of them finished experiments. We had 2 that didn't finish the whole drive due to simulator sickness, but also experiences slightly challenging for getting the regular drivers to actually talk about what they observe using think aloud protocols. So for the VTI experiment, we decided to use driving school instructors that are used to verbalize the thoughts and talk about what they see and so on. Some had limited experiments of being a school instructor, but some had quite extensive, as you see. So with that, I will leave to T to continue and give us some more on the results.
Okay, thank you. So now we move to the exciting and very interesting part, the experimental results. But before presenting the result, I would like to briefly explain how we measure the subjective perception in the 2 experiments. So in both studies, we analyze the post-scenario questionnaire data. However, the scale design was slightly different. In the TUM experiment, we use a 7-point Likert scale. Participants evaluate 4 aspects of the pink vehicle, and in the VTI side is the red vehicle. So the participants should tell us how predictable the pink vehicle behavior was, and how perceived the safety compared to a human driver, and how realistic it is appear compared to a human driver, and also how aggressive is totally the driving styles. And the study, so I would like to say the study was conducted first. So at this stage, we mainly tested the earlier version of the i4Driving model and also the experimental design itself. And based on the participants' feedback and also our experimenters' feeling, we refined and simplified the questionnaire for the second study in VTI. In the VTI experiment, participants have to provide quick assessment during the Turing task. So we reduce the scale from 7 to 5 points to lower cognitive load, and we also removed the aggressive item. In addition, instead of asking participants to compare the vehicle to a human driver for safety or realism, we asked for a general adjustment. For example, they should only ask if the vehicle behaved predictably or not, if the vehicle behaved in a safe way or not, if the vehicle behaved human-like or not. Yeah, and based on the analyze method, we used a within subject design. With multiple factors, and because the data did not meet the normal distribution, we applied the aligned rank transfer ANOVA and followed by a pairwise post hoc text. And on the left side, you can see the TUM data from 30 regular drivers. On the right side, you see the VTI data from 70 driving school instructors. So let's first look at the effect of the scenario type. At TUM, scenario had a significant effect on perceived safety. At VTI side, scenario had a significant effect on both predictable and safety. So this means the participant actually could perceive the clear difference among these 3 scenarios. But it's actually not surprising because the scenarios are varied and different. Now we look into the key factor, agent type. At TUM, agent type showed also a significant main effect on all 4 variables, predictably, safety and realism, and also aggressiveness. At the VTI side, agent type showed only significant unpredictability and human likeness. So in other words, participants will able to distinguish between these two agent types. However, if we get a closer look at the post hoc results, here from the Turing side, overall, participants tend to judge the human agent as more predictable, safer, and more realistic, but less aggressive than a i4-driven agent. You can see clearly here from the purple box, so the box plot. Across all three scenarios, the human agent constantly received a higher rating than an i4 driving model. And if we compare the scenarios, scenario B generally performed better than scenario A and C. Because in scenario A and C, the participant has a chance to directly interact with the pink or red vehicle. But in scenario B, the participant can somehow only observe directly what the pink vehicle did. And then, so however, focus on the realistic i4 driving model performed also significantly differently than the human agent across all scenarios. And then now we can also examine there is a similar patterns in the VTI data. So participants will still able to distinguish between agent types, especially in predictable and human likeness. However, you can see the rating range from human driver here, the paper box, shows also relatively large range. The experience of the is wider, so this means this is also a less agreement among participants. And interestingly, here is the mean rating for the i4 driving model are above the average of the rating here. So you can see here it's actually above 2.5. Yeah, so this suggests that even though their differences exist, the model was generally evaluated positively rather than negatively here. And to give us overall the impression how reliable the rating from the participant, we derived the response of the realism into two categories. We rating 1 to 3 were classified as not realistic, and rating 5 to 7 were classified as realism. And when we compare this classification with the actual control with the vehicle, the and overall the accuracy was only 65.3%, and we also observed 40 false positives, and this means in many cases participants judged behavior controlled by human driver as also not realistic. However, this comparison should be interpreted very cautious, because distinguish was it's controlled by human or not is not the whole task of the participant. Okay, so let's get to more deeper insight into how participants formed their judgment. We analyzed the think aloud protocol data. During the whole driving task, participants would ask to give us what they observed, what they plan to do, and how they evaluated the behavior of the pink or red vehicle in real time. And each participant could have 3 opportunities to test the vehicle's reaction or the response. And so this think aloud protocol allow us to give more details about what the model performed. And then I jump to our analyze in Turing side. So in scenario A, the most frequently among comment is the participant didn't. So when the participant didn't give the way to the pink vehicle from the merchant side, the pink vehicle continued to driving on the shoulder. So this participant perceived this behavior as unrealistic, but this issue was later addressed, also improved by VDI side. And another comment is here also the pink vehicle braking on the motorway before accidents, and also the behavior of the pink vehicle have not efficient acceleration after entering the motorway. And in the scenario B, participant reported that the pink vehicle accelerated too quickly at the beginning, but sometimes exceeds the speed limit. However, because in the scenario B, the pink vehicle need to overtake the truck vehicle in front of them. But after the overtaking, acceleration becomes not so notable. This inconsistency was perceived as unrealistic by participant, and also some participant or mentioned the lane change duration was too short, and others mentioned that the vehicle decelerated during the lane change, which they thought it's unnatural. And in the scenario C, the most critical issue was the gap acceptance behavior. You can see the pink vehicle will drive from this side, and the pink vehicle took a small gap and cut in front of the participant very quite sharply. Participant feels that it's not the vehicle didn't consider the behavior of the following vehicle in the neighborhood lane. So this lack of interaction awareness appeared very not so realistic. Another frequent comment was that the two vehicles drove too long parallel on this two lane, and participants were not sure or not uncertain about what the pink vehicle would do next, and this also reduced the perceived human likeness. So overall, this think aloud protocol from scenario A, B, C give us the highlight limitation, firstly to our experimental design. So sometimes, for example, here I highlight the yellow comments. So this experimental setting up to allow us let this two pink vehicle could interact directly at the right time. But this experimental design also let the participant feel unrealistic. But this is not the issue from the model performance. It is the issue from our experimental setting up. And this, what I highlight here in the red mark, we have also addressed this issue in the VTI experiment. And yeah, so now I will give the floor to Johan.
Yes, thanks, T. So fresh out of the box, since we did the VTI experiment a little bit later, the Think Aloud protocol results are arrived just this week. But similar to remember here, we had the two different settings. So we had this more careful and competent setting and this less cautious. The comments regarding A and C was very similar, so I grouped them together. So for the careful and competent, it's the strengths or the perceived strengths is that it seems to resolve large gap situations well, or yielding a cooperation when the situation is very clear. It's done in a good way, and it seems to be robust you cannot trick. If you try to provoke it, it seems to be not taking risky chances and so on. While the less cautious ones is perceived to accept more gaps, taking the gap more often, even if it's smaller, and also resolving the weaving when the margins are clear. While the perceived shortcoming is that it's very passive pre-merging behavior of the careful and competent one, which kind of mirror breaks or kind of slows down and not accepting the invitation to merge, or if you try to do with the indicators or slowing down to kind of give a social cue on kind of go ahead, take the gap, it's not thought of doing that. It's also not using the indicator or very late use of the indicator, while the less cautious one seems to be more issues on after the merge, that there might be dropping in speed or braking when it has merged in front of the participants. But also here, similar comments on the indicators. So the difference is mainly that there's maybe a too cautious pre-merge behavior of the careful and competent driver, which prolongs the conflict, while the less cautious is accepting gaps more often, but maybe do a little bit strange things in the post-merge behavior. So some things are similar, as you heard from T, and some things are new or different. If we look into scenario B with a truck platoon, and this, as we said, the scenario is slightly different. We had several trucks here and possibilities to merge in between, and we also put the agent already in the left lane. In order to get this scenario working, the agent was placed at a slightly lower speed, and that was experienced by as a perceived shortcoming, that they thought that the vehicle was driving too slow. So that's more of an experimental design issue than it's actually a problem with the model. But it's also thought that the careful and competent was maybe more cooperative and helped out, moving to the right and helping out, while the less cautious one was not felt like that. It was ignoring social pressure with approaching with high speeds and so on, and sometimes changed lane to the right very fast. Even the careful and competent one was also thought of not reacting to social pressure. But here one should keep in mind that flashing lights or the horn, that's not something that the model currently take into account. So it's only the high approaching speed or driving close that would have an effect. So there's not really clear differences here for scenario B as it is for A and C, but there are some. In VTI, we also had this post-agent questionnaire. So if you remember, we drew all the scenarios with one agent, and then after that we took a break, and we have RDW in the consortium, and they have these vehicle inspectors that work on trying to assess ADAS systems and ADS. So they have developed this test matrix where they have a 4-item scale going from really bad driving, shouldn't be on the road, to acceptable for basic driving, similar to a newly licensed driver, or very competent experiment driving, to optimal or fully compliant. So it's not really a linear scale, it's maybe rather exponential. And that one we tried to test to use here, and then we asked 5 different questions from this test matrix. If they think that the red vehicle recognized important traffic cues as road signs and change in situations on, if it drove at the appropriate speed, if it drove smoothly and decisionally, if it used the available road space efficiently, helping out in merging and so on, and if it showed defensive driving by allowing your vehicle sufficient space, even in situations where the participants maybe drove unexpectedly or pushed. So this is shown here in the terms of bars. So we have here 3 of the 5 questions, and we have the very green color is this yes, optimal, fully compliant, and the more whitish colors is then bad driving or newly driving license situation. So for the first one, if did the red vehicle recognize important traffic cues, there's a clear difference. So they generally think that the human drivers were doing that in a good way, and you can see here that it's not as high rated for the 2 i4Driving versions, and here it's also a statistical significant difference, which is not the case in the other questions. Because if you look then on if we use appropriate speed, we can see that it's still higher ratings for the human, but it's quite good ratings also for the i4Driving models. The same goes for if the red vehicle drove smoothly and decisively. Similar for how well they use the available road space, or if they show defensive driving. Even this defensive driving is maybe the one that looks most similar in terms of shares. So this also strengthens the same picture as Steve was talking about, that maybe the human agent is rated higher, but it's also that the i4Driving models are rated quite high in many of the cases. Also some results here from this open-ended questions at the end of the drive. It was clear that this setup with the repetitions improved the driver's understanding of the red vehicle's behavior, so it made them easier to predict and exploit how the red vehicle would respond. And it's also that many say that they become bolder and learned how to provoke or test the red vehicle later on in the experiment. So it was good that we have the balanced design, so it was not the same order of scenarios, same order of agents all the time, because that would have been maybe a problem. We also had a question, even if we didn't tell them that they were a human that control one of the vehicles in the beginning, we kind of indicated it's in this open-ended questions and asked, would you believe that some of the red vehicles were controlled by humans, why or why not? And most of the participants answered kind of cannot say, or maybe sometimes stating that the red vehicle occasionally maybe behaved as a human, but other times not. And 6 said no, they don't believe it because the scenarios were too similar to see any difference, or the red vehicle was too passive and interacted too late in general to be a human driver. And only 3 kind of said, oh, yes, I think the vehicle in block X was a human driver, and all those 3 that did that answered correctly. But we didn't ask them, we didn't tell them that there were a human in one of the block and ask them kind of which block. So it's only 3 that attempted to guess, and they were not the other ones were not asked to guess. So what are the conclusions and takeaways then? So we have divided into 2 parts. One is more on how realistic is the i4Driving model perceived to be. So coming back to our 4 research questions, to what extent can participants distinguish between the human and i4Driving models? As we see, for many of the scenarios, participants observe clear differences between the agents, and the T's table there, you can see that the rating is different, and the human model is rated more human-like than the i4Driving model in general, but there are also cases where the human agent is rated less human-like, and the i4Driving model is maybe rated high and also in several cases. So it's not perfect, but it's also quite good. Looking into what aspects of the driving behavior is influencing this judgment of human likeness or not, then predictability and safety seems to be giving quite interesting additional insights to the ratings or questions on human likeness. And in the Think Aloud protocol analysis, we could also see that defensiveness is also influencing how human-like. They think the driver is this kind of mirror breaking and not taking the gap when given and so on, being very defensive is thought to be strange. So if we look on the method side instead, kind of how useful is it to do this kind of exercise, doing a Turing-inspired driving simulator experiment? So we had this question, to what extent is it a good evaluation method? We think that it provides quite interesting, valuable feedback for behavior models or improving behavior models, or if one would replace the human driving behavior model with an automated vehicle logic that it could provide valuable feedback. Because with this subjective evaluation, we get the complement to this traditional objective validation, so we get more details on why there might be a difference. There might be that this available interaction time was too short or too few repetitions to get a complete impression of the agent. But I think for sure when we took one agent at a time, as we did in the VTI, it was better than what we did in the TUM experiments. And how can these insights then that we gain guide the further refinement of the i4Driving models? I mean, in some of the cases, this kind of comments on indicator uses, whatever, maybe it's not that important for doing traffic simulation because it's not model, or is it the information is flowing directly from a simulated agent to another. So when there's not a real human involved in the loop, then maybe it's not needed. Well, on the behavior modeling side, this tactical driving behavior, tactical timing in emerging situations is something that come up several times, and this communication kind of, I create a gap, but you don't take it, and so on. So that might need further refinement. And if one would redo this, if we kind of know all this when we started, or if someone of you would like to try to do this, the takeaways I think we noted down is that it would be good to have longer interactions and more repetitions. Maybe have the possibility to repeat until you are satisfied as a participant. Kind of, now I tested everything. Now I'm happy. Also, in order to know how to interact, it would be good with longer practice sessions for each scenario to let the participants create their own plan for testing so that they can use the same plan for all agents. There were also some suggestions, maybe one could start with more simple scenarios and gradually make the scenarios more complex. And I think we also can conclude that using these expert drivers like driving school instructors, we also did some tests with Dutch vehicle inspectors, so that they are well suited to verbalize their observations of behavior while driving as well. But it was a little bit more challenging using the regular drivers. Yes, and if you would like to know more, then you're more than welcome to contact T or me, and there were not possible to do this with a lot of help from other persons at VTI and TUM, and also other colleagues within the consortium. There's to create the setup and all this and get it to work. I probably missed a couple of people here as well. I don't think our confederate human drivers is on the list, but maybe they should remain secret for all time.
Thank you very much, Johan and T. I think, as usually, we keep reminding our webinar series to get your participation. So thanks a lot. I think it was very nice to finally show to the world what we have been testing and how was the reaction to the human driver and to the models in the Turing test. And now we have some time for some questions from the audience or comments. So please, the floor is open. Thank you to our speakers once again. And now it's on your side. It's the moment to ask everything to make Johan and T lives difficult.
There are data sources publicly available. Yeah. No, I don't think so. And there's also a question what we could share or not, but we could probably share some parts, maybe not the recordings of the For example, I don't know if we can share the transcripts or so on, but they will be in Swedish and German as well. So maybe it's more of the conclusions that are interesting anyhow. But of course, if you're interested to know more and utilize the data, so something we're clearly open for discussions and collaborations. So don't hesitate to ask. We can also say that we of course recorded the speed profiles and all these things, but they're not really interesting to study here because some of these participants, they provoked quite a lot. They drove until the last meter on the weaving segment before kind of merging and so on. So they, the situations are quite extreme sometimes, which we were also worried about that they would not test. They would drive mainly safe and cautious or competent that they do a normal case and not provoke or test the participant vehicle. But that's I forgot to write that on the slide, but that was something that worked quite well. That they took the opportunity to test and interact for sure.
And what was the biggest difficulties that you had?
I mean, integration-wise, just to get it all up and running was a little bit of a challenge with different time synchronizations and so on. But I think we managed quite well with this synchronization in the end. But it was a little bit tricky there. I think also on our side, since we use driving school instructors, we got more of all of the ones kind of in local in Linköping than there was. We were happy that there were also some people coming from Gothenburg and Stockholm and other things, because it's of course the limited number of participants. I don't know what was the main challenge at the TUM side, T.
Actually, the TUM side is the synchronization because we don't use the open source software in our simulator. So we did a lot of technical change in the simulation, in the driving simulators. And then also, because our mod is the i4Driving model, so we only tested the early version of i4Driving model, and we have some synchronized also with our model developer from TU Delft that they give us a lot of variable tips, and it's it's challenging.
We have a very good question from Masood here. Thank you for the presentation. Since all surrounding vehicles in the simulator are algorithmically controlled in one way or another, how can we be confident that participants truly perceive and distinguish between a human driver and i4Driving models? So I think, I mean, the extra vehicles there, they were quite far off, and so you mainly interacted with the red vehicle, and it was distinguish different colors. I'm not so worried about that. The judgments were about other algorithmically controlled vehicles in the environment. Then, of course, since we asked them to assess how human-like the automated driving logic of the red vehicle was, we didn't ask them to say if it was a human driver model or a human. We cannot be sure, but at least the descriptions of the red vehicle's behavior and how it varies when it was human and i4Driving, I think we can conclude that we can be quite confident that they really describe the difference of the behavior of human or the i4Driving model.
Then we have another question.
How to transform abstract answers and statements in the think aloud protocol into parameter settings of models. Yeah, that's yes, it's for sure. It's more of a validation rather than trying to do a calibration, and that was kind of not maybe the main requirement. It could also be that some of the things identified is not just that you need another parameter setting to make it more human-like. This kind of making the tactical driving behavior better in terms of accepting gaps and so on. That could also be that there are some tactical driving behavior part of the model that needs to be further developed, I would say. So I would rather see this as a validation activity rather than a calibration activity. Yes, thank you for the presentation. Do you think this full testing and evaluation procedure is necessary for each driving model you would like to assess, or would it at the same point also be possible to evaluate a new driving model to driving models that have been assessed using the Turing approach? Good question. I guess one come back to, don't we, that if you, how would you compare? Because then you're coming back to comparing trajectories between the two models, and then you get into this objective error metrics, and then even if the error metrics then are similar, then will it be perceived as realistic or not? Not sure, but we also, when we had these vehicle inspectors there, we also concluded that if you would really like to test automated driving, then maybe this is more in order to find out which scenarios and how to do the testing. So by doing this Turing test with one driver model, maybe you can develop, this is what you should do and test, and then you only apply that when you're testing other types of driving models instead of testing every driving model for all the different possible scenarios. Even lots of interesting good questions here. Yes. Are we confusing realism with randomness in the experiments? Can a noisy model with randomness pass the test without proper anticipation or planning? Is consistency penalized by the participants even when it reflects competent behavior? 3 questions in one. Yes. Where to start? I mean, the randomness to a large extent comes from what the participants decide to do in order to interact. So they decide to, let's see, if I give a gap, will it use it or not? If I try to go first, or if I try to provoke and not let it go here, or whatever, what would happen then? And see how that vehicle then reacts to that one. So I think realism in that part is kind of in each situation. I think there is actually judging or trying to look on how safe or predictable or human-like that behavior is. So I would say that in that case, we're not confusing realism with randomness, if I understand the question right. And in this case, we are also having, I mean, a noisy model depends on what you mean. I mean, noisy here. Normally, the randomness in this type of model is within the parameters that you assign, so that you assign different drivers, different parameters, and then you have heterogeneity. There could also be, of course, randomness in the decision by the model in a specific situation, and then you would maybe need more than these 3 repetitions to find out if this was just a bad random decision. I'm not sure that consistency is penalized by the participants. Okay, yes, referring to randomness decision making, I think that there is limited randomness in the decision making. I don't think we have any of the TU Delft people works most with the model development, but I think it's main part that it's of the randomness is in the assignment of the parameters and the heterogeneity of the drivers. But that's a good point. If you have a lot of randomness in the decision making, kind of stochastic random numbers in whether you accept the gap or not, then maybe you need more repetitions. Something to add, T, on this one?
Any more questions? Nice, both of you, if you have any question to each other, that's also possible. Although I think you had many during the last 3 years.
Yes, yeah, there have been lots of discussions. So I said it was lots of people at VTI and TUM for conducting the experiments, but we had lots of discussions with the people from TU Delft developing the model and Janina working on calibration validation, RDW with the vehicle inspectors and so on and so on. So this has been a long discussion on how to do this, and it was really nice that we had the possibility to do 2 experiments and also make a test and then revise for sure. A different type of driving simulator experiments where we use the participants as sensors, which have been quite nice.
One more question. Can the parameters of the model be tuned with data to make it more human-like?
Yeah, I guess that's what all calibration is about, but the calibration is then mainly comparing this error metric on kind of how well do you get the position, speed, acceleration, and so on. I guess what one could use this kind of setup is that you could change parameters and then as a model developer run and interact and see what you think, and then change it again. So use it in kind of a online calibration, but then it's your subjective feeling, so you can buy. And we did a little bit of that as well ourselves, just to see, okay, what if we change this parameter, increase the time gap or lower the time gap acceptance and so on, to see how is the difference in the behavior. So but I guess that's more in order to get a better understanding on how sensitive the perceived realism is to changes in the parameters.
Perfect. Then I think I don't see more questions coming up. I think it's the moment to thank you one more time to our speakers. Thank you for all the ones that attended our webinar, and I hope to see you again in the upcoming ones. We still have 4 more to go. It was a very long project and we have many things to tell. So thank you very much, everyone.
Thank you for joining.
Thank you too.